Thank you, everyone, for here. Thank you, Professor Nord, for the invitation, the Molecular Foundation, Futures Foundation. It's really here, surrounded by an august set of speakers and chemists. I feel a little out of my element being a humble water chemist, but I'll try to tell you a story today that I call Adventures in Water Treatment. I guess I should start by saying I first fell in love with water. I grew up near the ocean outside of New York. I spent a lot of my time down there looking at water, contemplating water, learning about water, seeing the life in water. And then I fell in love with chemistry because the place I lived was only about 2 or 3 miles away from Cold Spring Harbor Labs, and I was fortunate enough that one of the scientists that they hired at Cold Spring Harbor Labs was married to a woman who they wouldn't hire there because the policies at that time. So I had a PhD teaching me high school chemistry, and she inspired me, and I fell in love with chemistry. And I decided that I would put these two loves of mine together, the love of water and the environment with the love of chemistry. And so I went to college and I took Introduction to Chemistry from a Nobel Prize winner, Roald Hoffman at Cornell, and I fell out of love with chemistry. And that was because the kind of chemistry that you learn in freshman chemistry at the university tends to be a little dry. It tends to be about the periodic table. It tends to be about all kinds of things that, for me, was very hard to relate to because I wanted to solve problems related to water. And I didn't see a path to get there. Fast forward a few years, taking courses at the university, going out, trying to clean up hazardous waste sites and improve water, I fell back in love. But this time, I fell in love with environmental chemistry. And so today, for those of you in the audience who are high school students who have this nascent love of chemistry or wondering what to do with it, I want to give you another option. You can certainly go and work in theoretical chemistry. You can think about the structure of water. You can think about it at a molecular level. But you can also take the things that you're learning about chemistry and apply it to solving pressing problems that face humanity. To put it into perspective, I've been hanging out with engineers for a long time, and we think in terms of quantity. We think about mass balances, we think about amounts, we think about whether something will be economically practical. And so I tend to think in units of cubic meters. So when I think about water, I think about a cubic meter. This is an image of a tank, holds about 1 cubic meter of water. You've got a Labrador retriever for scale there to give you an idea, like something like this, a tank full of water. How many of those do you think it takes each day to live your life as an American living in the United States here or wherever you are overseas watching this? What do you think? How many? Do you think you need a half of one of those, a tenth of one of those? What if I told you you needed 7.8 of those to keep you alive every day? That was the amount of water that was being used to keep you going. Think about this table here, this whole volume here, fill it with water, and every day someone has to come up with that much water for you. That's why humanity has taken over the hydrologic cycle. That's why we have dams and reservoirs everywhere. That's why when Professor Sedlak was talking on the first day about snowpacks and disappearing reservoirs, we see this huge footprint of humanity on the water cycle. Luckily for people like me who think about water treatment, not all of that water is treated. About 90% of it goes to agriculture to grow your food, and some of it goes to cooling thermal electric power plants. But of that water, about a half a cubic meter a day has to be treated. That's the water that gets put into the pipes and sent to your home in a city. You can't just take that water out of a reservoir or out of a river. Sometimes you can take it out of a well without treating it. Most of the time, you have to settle the particles out, you have to filter it, and you have to disinfect it to make sure that it's safe from a microbiological standpoint, both that the microbes don't grow inside the pipes and cause the pipes to corrode and foul with all kinds of nasty stuff, but probably more importantly, you need to disinfect it, a form of treatment, so that when you encounter that water, you won't get sick from the effects of a pathogenic microbe. So about 100 gallons per person per day is a typical amount of water that cities supply to people living in California. That's a lot of water, and if you're going to treat it, it had better be darn cheap to treat that water because you're treating so much of it every day. So you have to think about super cheap, inexpensive, foolproof technologies to make this water safe. It's kind of weird that we treat all that water when half of it ends up on our lawns and in our gardens. So the green part of this pie chart shows you the fraction of the water in a California city that goes to either residential irrigation or institutional irrigation. So the ball fields around the campus here or around your local shopping mall or along the highway, the golf courses, as well as the water that are used in people's homes, account for about half of the water. It still has to be treated because it goes into the pipes, but it's not really going to get anyone sick. The other half of the water is mainly used indoors. You can see a small amount of it used for industries. We don't do a lot of manufacturing in our cities in the United States, only about 6% for industry, a small amount for energy production, cooling towers, server farms, things like that. Often they have their own water supply. The other half of the water primarily gets used inside of our homes. And if you think for a moment how water gets used in your home, it's mainly going to the washing machine, the dishwasher, the toilet, and the shower. And there's a little bit of water that you drink. Maybe there's something like 2 liters a day that actually go inside your body and that you drink. And yet we treat that water to make it microbiologically safe because you don't want to shower in water that's full of Legionella bacteria. You don't want that stuff all around your house when you're washing your hands. So we treat it all, and it's also impractical to send 2 separate types of water to our homes. We usually have this one set of pipes that comes into our house. So we have to treat all of that water, despite the fact that most of it goes out in the garden, most of it goes down the toilet or in the washing machine, for those 2 or 3 liters a day that actually goes inside of our body without any further treatment. Now, I got involved with this field of water chemistry because of a love of water molecules. And when I think about water, I do tend to think sometimes like a physical chemist. When I think about a glass of water coming out of my faucet, I realize that it's like 55.5 moles per liter of water. If I think on a mole fraction basis, it's close enough to say it's got a mole fraction of 1. It's 99.99999% water. But it's that other stuff that's in the water that is the bailiwick of someone who works in environmental chemistry and someone who thinks about water treatment. I have to think every day about all of the other stuff in water that could cause problems to the quality of the water when I think about designing a water treatment system. Let me first think about the things that make water tasty. So if you remember from Professor Zare's talk yesterday, he showed heating some water and condensing it on the bottom of a watch glass, and there was a little bit of hydrogen peroxide in there. Well, if you were to take that water and taste it, it would taste nasty. Not because the hydrogen peroxide, but because it's pure water. So if you've ever had the urge to drink distilled water like that you maybe buy to put in the iron at home, or heaven forbid, you drink water in the lab, that ultra-pure water that you need for some chemical experiment, it's not going to taste very good. Because humans have evolved in a world where water contains millimolar concentrations of things like calcium and sodium and chloride and bicarbonate. And this is what gives water its characteristic taste. So if you look at the side of some of those like nasty brands of bottled water, I won't name them because this is going to end up on a video sometime, the manufacturers, the soft drink manufacturers, what they do is they take tap water from whatever city they're in, they subject it to reverse osmosis to take all the salts out, and they add in some calcium and carbonate and a little bit of sulfate to make it taste like it actually comes from a real place. So that's part of making water tasty. But those people who make that synthetic water are missing something because they often forget to put the things back in the water that make the water healthy. So, for example, when Israel adopted wide-scale seawater desalination, when they substituted their natural water supplies with desalinated seawater, it was too expensive to add magnesium back into the water. They added calcium back into the water so it wouldn't corrode the pipes, but they couldn't afford to add magnesium. And so now in Israel, people have magnesium deficiencies that are leading to elevated risks of heart disease. And there's talk about giving people supplements in their diet to give them that magnesium. In places where there are reasonable concentrations of fluoride in the water supply, that fluoride is wonderful. It makes children's teeth healthy. But in places where there are deficiencies in the fluoride concentration or when people use desalinated water as their water supply, you either have to add fluoride to the water supply, like we do in the United States, and you certainly have to use fluoride mouthwashes and fluoride-containing toothpaste. And finally, there's an emerging hypothesis out there that water supplies that are deficient in lithium, in those places, people have a higher rate of suicide and violent deaths. And that's because lithium, the main source of lithium, is the water supply. You don't get a lot of it from your food. So there are things in water, and we're still learning about them, that are actually needed for our health. But I'm interested in the things in water that could compromise our health. So certainly thinking about water quality, I think about things like nitrate. So we heard about the Haber-Bosch process yesterday. Well, when farmers use nitrogen to fertilize plants and crops, some of that nitrogen gets away. It makes it into the groundwater or the surface water. And if it makes it into our water supply, it can be bad for our health. So we spend a lot of time treating water to take nitrate out. Or some places, the geology is such so there are high levels of arsenic, and so there could be elevated levels of arsenic in the water supply, not just in Bangladesh, which is the classic place that people think about it, but in the American Southwest. So if you're in New Mexico or Southern California, often the water supply is elevated in arsenic. And of course, we've all heard about Flint, Michigan, where the pipe network that delivered water to people's houses underwent a process of corrosion, and that released lead. And that lead made people sick because it's a neurotoxin. I could talk about these inorganics, but what I want to talk about today are the organic chemicals, because I want to tell you about my adventures in treating organic chemicals in water. Some of these organic chemicals come as a result of the water disinfection process. So we often add strong disinfectants to our water. We add chlorine, we add ozone. Sometimes we treat water with ultraviolet light to kill the pathogens. And in the process, we make things like dichloroacetonitrile, that's a chlorine disinfection byproduct, or we make things like crotonaldehyde and nitrosodimethylamine, NDMA, which I'll talk about today. But there are some other chemicals in our water supply that get there as a result of industrial activities. And the ones that you've probably heard about in recent months and years are the PFAS chemicals. I show you here PFOA and PFOS, two examples of these chemicals that are on stain-resistant garments that people often wear, or that are in foams used to fight fires at airports and oil refineries. And those so-called forever chemicals make it into the water supply, and they're toxic to people at very low levels. In fact, those of us who are water chemists are waiting for the US EPA to come out with the allowable safe levels of these compounds in water. They're probably going to be in the 1 to 10 nanogram per liter range. And so here we span this range from 55.5 moles per liter for water all the way down to like 10 to the minus 12 or 10 to the minus 13 moles per liter as an acceptable level for these PFAS chemicals. And so for me, thinking about water, it's a lot more than just the quantity of water. It's the quality of water. And the quality of water requires us to think over many, many orders of magnitude about the kinds of things that are there. Now, as someone who's still in love with chemistry but wants to solve problems, I think about the different approaches that we can use from chemistry to solve this problem of organic pollution. I'll show you today that sometimes it's solved with physical processes, but I love the concept of oxidizing these chemicals. So I think about oxidative water treatment. So I want to give you 3 adventures today. The first adventure I'm going to start with, I'll call Adventures in Remediation. This is where I started. This is where my love for water chemistry came about. This was my inspiration because growing up in the 1970s and 1980s was a time when people first discovered that chemicals used by industry were getting into the water supply and causing people to get sick. And these chemicals, this is a picture of a place called Valley of the Drums, which is one of the notorious chemical spills or chemical disposal problems of the 1970s. These contaminated waters, and we had these hazardous waste sites called Superfund sites that had to get cleaned up. And I got involved with that right out of my undergraduate with a bachelor's degree, helping to clean up hazardous waste sites in New Jersey. And believe me, I didn't get anywhere near finishing that. I went back to graduate school before I could even make a dent in that problem because there were so many of them. And at that time, this is the technology people were using. It was called pump and treat. It was a very primitive way of cleaning up groundwater. You basically stuck extraction wells in the ground, and you pumped the contaminated water out, and you used some sort of physical process to take the organic chemicals out of the water. You either absorb them on an activated carbon, like those cartridge filters that maybe you have in your refrigerator for making the water taste better, or in something that seems like incomprehensible today, air stripping. You basically took advantage of Henry's law constant, and you let the organic chemicals go into the atmosphere, and you let the people who kept the air clean worry about them. I don't think we do that as much anymore. But this process of cleaning up hazardous waste sites by pump and treat turned out to be extremely expensive. We spent tens of billions of dollars in the United States cleaning up hazardous waste sites, and we'd pump and treat, and the contaminants would keep coming out of the ground. And so we realized that we needed other approaches. One approach that was feasible for removing certain like gasoline spills, the hydrocarbons that come out of gasoline, or some of the halogenated solvents that were contaminating groundwater, was bioremediation. We would coax the microbes to break down those organic chemicals into carbon dioxide and water. And that's been effective. But it doesn't work for everything, because some of those environments are inhospitable to microbes, and they can't manage to evolve and develop the metabolic machinery to break down those chemicals, and sometimes they're just too slow. And so a technology that I found particularly intriguing, which was developed in the late 1990s, just as I was kind of launching my research career, was something called in situ chemical oxidation, or ISCO. And this, to a chemist, seemed like a great innovation, a great novelty. I didn't have to understand microbiology. I didn't have to understand the vagaries of hydrogeology. I just had to put in some wells and start pumping strong oxidants into the groundwater table. And those strong oxidants would react with the organic chemicals, and they'd turn into carbon dioxide and water. At least that's the thought that people had. Now, in these early days of ISCO treatment, engineers went out there fearlessly, and the first oxidant that they stumbled upon was hydrogen peroxide. Hydrogen peroxide was a great choice for cleaning up hazardous waste sites because it's inexpensive, it's soluble, right? You can get like a 3% solution of hydrogen peroxide from the pharmacy, or industrially you can get a 30% solution of hydrogen peroxide. It's relatively stable, so you could put it in a truck and take it to the hazardous waste site where you want to use it. And it goes into the ground, and the idea was that in the ground it would decompose to different radical species. We heard about these reactive oxygen species yesterday that are so highly reactive. These are the kinds of things that cause the inflammatory response in the body, or sometimes lead to cellular aging. Well, those same processes, these reactive oxygen species, can also be used to break down chemicals. In the early days, people showed up at hazardous waste sites, about a mole per liter of hydrogen peroxide into the ground, and sometimes it worked, and sometimes it caused the well to melt. An exothermic reaction took place, which generated so much heat that the PVC pipes of the wells would melt and no treatment would get done. And it was discovered that that process through which the hydrogen peroxide decomposed into hydroxyl radical was catalyzed by the iron-containing minerals in the subsurface soil. So if you've ever dug up in your garden the soil, you've probably seen that like characteristic reddish-brown color. Oftentimes the red color is coming from iron oxides. The brown-black color comes from manganese oxides. These are the common minerals that we find in our soil. They're some of the most abundant metals in the Earth's crust. And so we had a catalytic reaction where the iron 3 oxides, which is the normal state that we find iron oxides in, would react with hydrogen peroxide to make the hydroperoxyl radical, HO2 dot. The hydroperoxyl radical will react with itself or with superoxide to undergo a dismutation reaction to make hydrogen peroxide. But the iron 2 produced in the reaction would react with hydrogen peroxide to make hydroxyl radical. And hydroxyl radical is the vacuum cleaner, if you will, of organic chemicals in the environment. In the atmosphere, when ozone decomposes or when sunlight hits the troposphere, we generate hydroxyl radicals. That's how the hydrocarbons emitted from gasoline end up breaking down and forming smog. And in water, when we generate hydroxyl radicals, they react with just about every organic compound, not all of them, but just about every organic compound at near diffusion controlled rates. And if you've never thought about like the Lewis dot structure of hydrogen peroxide, it's shown here. When it reacts with iron, you can see that the iron gives up one of those electrons. The hydrogen peroxide gives up one of those electrons. And you form hydroxyl radical. You have that unpaired electron. And that unpaired electron is what makes hydroxyl radicals such a strong oxidant, because it wants to grab another electron and become hydroxide. And when it does, the organic compound that gives up that electron will become a carbon-centered radical or some sort of other radical, which will undergo a chain decomposition process, as I'll show you later, to ultimately make carbon dioxide and water. Now, when we started looking at this, we started studying this process, we were surprised at how inefficient it was. We would add close to a mole per liter of hydrogen peroxide to soil, and we would degrade micromolar or less concentrations of organic chemicals. And what we discovered after a few years of research is that there was another competing reaction going on, which didn't produce hydroxyl radical. It produced water from hydrogen peroxide. And that reaction was a 2-electron oxidation of ferrous iron to form an iron 4 species. I don't want to go into the chemistry of the iron 4 species, but the iron 4 species either reacted with iron 2 or underwent another set of reactions and ultimately became iron 3 in water. And so there was this wasteful reaction happening, the blue reaction, in parallel with the reaction that was making the hydroxyl radical, which is what we wanted to do, the red reaction. And so we thought about the idea of like the efficiency of this reaction as the fraction of the hydrogen peroxide that decomposed on the iron oxides to generate hydroxyl radical divided by the fraction that we lost by both mechanisms. And what we found was that the iron oxides that we studied were incredibly inefficient. Their efficiency for hydroxyl radical production was usually less than about 0.2%. So we went and looked at all the different clays, all the different iron oxide polymorphs. They were all very inefficient. We could make some catalysts, and this figure shows you some catalysts that we designed in the laboratory. Our catalysts could have efficiencies of 2 or 3% on a good day, but we couldn't find a way to get those catalysts down into the subsoil where we were trying to do this treatment. We were stuck with the native iron oxides that were there to begin with, and we had this process which was incredibly inefficient. So something like 99.9% of the hydrogen peroxide that we added to the aquifer just converted into water and oxygen ultimately. That's why when you add hydrogen peroxide to a cut, you see it bubble, right? It's that dismutation reaction happening, catalyzed by things in your skin. So being a little bit discouraged by this, we thought about maybe rather than hydrogen peroxide, we would look for a different peroxide. And the peroxide that we stumbled on was peroxydisulfate. So you can see here I've highlighted the peroxide bond in peroxydisulfate in, I guess that's yellow or green or whatever it is, depending how colorblind you are. It's basically the same bond in hydrogen peroxide. Instead of having a hydrogen attached to the oxygen, you have an SO3. So it's like taking 2 sulfate ions and gluing them together across a peroxide bond. And our hypothesis was that if we put peroxydisulfate into the ground, it would react with these iron oxides in this catalytic reaction, and we'd only have the red reaction, the one that made the radical, and not the blue reaction, which was the wasteful one. And now, instead of making hydroxyl radical, we would make sulfate radical. And sulfate radicals seem like almost as good as hydroxyl radical, because if you go into the physical chemistry literature and you look at the kinetics of reactions of sulfate radical with organic compounds, they're almost as fast in terms of kinetics, and they're almost as strong in terms of being an oxidant. So sulfate radical reacts with like 80% of the things that hydroxyl radical reacts with. If something has really strong electron withdrawing groups, like a nitrobenzene, it won't react. Just about everything else reacts. I had a patient sabbatical visitor named Urs Jans from City College of New York who spent a year with me. We tried to study these reactions, and they turned out to be so slow. These reactions, which for hydrogen peroxide had caused PVC wells to melt, when we did it with persulfate, we had to wait weeks and weeks and weeks and weeks for this to happen. So we got the idea from looking at engineers in the field that were trying to apply persulfate that maybe we would heat up this system and play around with the activation energies of the reaction. And we found that heating up this reaction without even the iron oxides present was a much more efficient way to go, because we could cleave that persulfate bond and make 2 sulfate radicals for each persulfate. And we could do this at modest temperatures, like 40 degrees centigrade. So now we had a way to deliver an oxidant that would make a radical with a very high yield into the subsurface. All we had to do was heat an entire groundwater aquifer up to 40 or 50 degrees centigrade. Now, the US military had been fooling around with things like this on cleaning up hazardous waste sites. They would stick giant electrodes in the ground and pump electricity through the ground to get frictional heating to go. People had thought about all kinds of things, but the thing that was really inspirational was an idea from some of our colleagues who worked on this ISCO technology for peroxide. They said, why not first treat the system with the peroxide, let that exothermic reaction heat up all the soil, and then put the persulfate in. And so that's what's done in practice now, to heat up an aquifer to get it ready for the persulfate, and this is what people do. Now, with this better oxidant in hand, we set out on what I think was the biggest challenge that we could find, and that was remediating PFAS. So this molecule here, 6,2-fluorotelomere sulfonate, you can see this is a surfactant. I show it in its neutral form. It actually exists as a zwitterion in the ground. It's a surfactant that's used in firefighting foams. So if an airplane catches on fire at a military base or an airport and they've got all that fuel burning and they're afraid of it causing tremendous death and destruction, the fire department shows up not with water, not with normal hydrocarbon surfactants, but they show up with perfluorinated surfactants, a material called AFFF. And this is the basis for a lot of the contamination of groundwater and drinking water that we see today with PFAS. And this compound is very easily treated or oxidized by persulfate. You can cleave the ethyl group you can see between the terminal perfluorofunctional group and the sulfur group really easily, because a sulfate radical reacts very quickly there. But then you're left with this fully fluorinated chain. And those carbon-fluorine bonds on that chain are incredibly stable. These are among some of the strongest bonds known in chemistry. So they're really hard for sulfate radical to break down. And it doesn't break them down, or it shouldn't break them down. But when we did our experiments on this AFFF compound, we saw them breaking down. We saw this perfluorocarboxylate chain getting shorter and shorter and shorter, as shown in this figure here. And what we figured out was that if we let the pH of the solution fall, because when persulfate decomposes, it liberates a lot of protons. It basically breaks down to sulfuric acid. And here we are adding like molar concentrations of the persulfate. So we're making tens of millimoles and sometimes molar amounts of sulfuric acid, so the pH is dropping very quickly. We saw that if the pH dropped below 3, we could actually break down these perfluorocarboxylates. And it turns out that there's a theory going around and a paper published on it that shows that the sulfate radical at low pH gets protonated, and the protonated form of the sulfate radical seems to have sufficient energy to break down that perfluorocarboxyl group. So we proposed the idea of remediating, cleaning up some of these hazardous waste sites that have these compounds in it using this technique. And the problem is that when you use this AFFF material, it also has the sulfonates, compounds like PFOS, and those don't react with this protonated sulfate radical. So we're now seeking other ways of doing it. We have some good ideas of, instead of using oxidants like sulfate radical, using selective reductants. And if someone wants to talk with me about that, I'm happy to talk with you about it at lunch. But that's kind of the end of my first adventure in water treatment of hazardous waste. My second adventure, my third adventure are a little bit shorter because I'm still in the middle of them. The second adventure is adventures in water recycling. Now, those of you who don't know, who don't live in California may not be too familiar with water recycling. Those of you who are not water people may not be familiar with water recycling, but there are kind of two types of water recycling that are done. The first water recycling is like you take the water from the sewage treatment plant, you treat it, and you use it on the golf course, or you use it on the highway median. You've probably seen these signs that say, being watered with recycled water, don't drink it. But the second type of water recycling, the type that California and Arizona and Singapore and Texas are investing millions and millions of dollars in today, or maybe billions of dollars, is potable water recycling. That is taking water that comes out of a sewage treatment plant and treating it to a point where it can be put directly into the water supply. And I want to tell you about my adventures in potable water recycling because this really is the future of how people who live in places with water scarcity are going to adapt to climate change. And it needs chemistry. So this is what we think about when we think about taking water from a sewage treatment plant and treating it to a point where it could be safe to put directly into the drinking water supply. We think about it as a multiple barrier approach where the first barrier is reverse osmosis. This is a technology that's frequently used for seawater desalination. So it takes all the salts out, and it takes all the particles out, and it takes all of the charged ions and non-ionized or neutral compounds that have a molecular weight greater than about 200 Daltons. Because it's not a size exclusion process, it's a water molecule diffusing through a polymer. So it's a wonderful technology, and you can remove things like PFAS, and you can remove a lot of the molecules I've told you about. But there are some molecules that can get through reverse osmosis. And in the second stage of this treatment, we use something called the UV peroxide process, which generates hydroxyl radical to break down any that make it through. By the way, the pathogens that might be there, the viruses, the protozoa, the bacteria, they get removed by the reverse osmosis process and also all of the UV light that's used in this chemical treatment process. This UV peroxide process is very similar to the one that we used for in situ chemical oxidation, except we're not using iron oxides to catalyze this reaction, and we're not using heat to break the peroxy bond. We're using ultraviolet light to break the peroxy bond to split hydrogen peroxide into two hydroxyl radicals. This technology was originally developed during that era of pump and treat groundwater treatment when people said, well, we don't want to be venting it to the atmosphere and activated carbon isn't the best way to go. So that's where it was first developed. But it's really come into its own in its use for potable water recycling. This is a picture of Trojan's UV Fox process. It's basically a pipe. The water's flowing through that pipe, and that pipe is jammed full of ultraviolet lamps. And a little bit of hydrogen peroxide gets squirted into that water before it runs this gauntlet of UV lamps. And in that process, lots and lots of hydroxyl radicals are made to this water that's already been through reverse osmosis. Now, I was very interested in this because I've been interested in hydroxyl radical reactions with organic compounds for a long time. And the first thing that I learned as a student studying hydroxyl radical reactions with organic compounds was that when an aromatic compound like benzene reacts with hydroxyl radical, you form a hydroxycyclodienyl radical, this radical species where you lose the aromaticity in the benzene ring, the one electron is abstracted, and then you get the addition of hydrogen to it, of water to it, or hydroxide, and then that reacts with oxygen. And so the unpaired electron, that carbon-centered radical that the benzene has become, gives its electron to oxygen, and oxygen makes hydroperoxyl radical, and we saw hydroperoxyl radical before, that just decomposes into hydrogen peroxide. And this is what I had observed all the time in the past, that whenever I treated an aromatic compound with hydroxyl radical, I hydroxylated it. But when we started to look at this a little more carefully, we saw that another pathway was here, a pathway where the oxygen bridged across the molecule to give us several additional pathways. Some of those pathways led to phenolic compounds or diphenolic compounds, but we could get this ring cleavage process in just one hydroxyl radical attack. So the thing that people often forget about hydroxyl radical reactions is that you need a second reaction to get that carbon-centered radical into a stable form. Quite often, the carrier of that radical is going to be oxygen. It's going to be responsible for the second oxidation step, and sometimes it can lead to ring cleavage in one step. And I got interested in this ring cleavage because I know from the biology of these things that these are very strong electrophiles, and I worried about them damaging proteins and DNA because those are nucleophiles. And so we developed a technique to look for these things in water, and that technique used proteins as probes to react with strong electrophiles in water. And what we discovered is that reactions of hydroxyl radical produced by the UV peroxide process produced a whole host of these aldehyde ketone compounds that have this unsaturated bond in them. And for the toxicologists and biologists, this was a real issue because when you have that unsaturated bond, it makes it much more toxic. So we found this UV peroxide process, when it reacted with aromatic compounds, was A, causing ring cleavage in the first step, and B, producing these unsaturated aldehydes. And so we went out to some of these advanced treatment plants, and we looked for them, and we saw that we often produced aldehydes. These are the saturated aldehydes, things like formaldehyde and acetaldehyde, but the unsaturated aldehydes were up here. And they tend to be 1 to 2 orders of magnitude more toxic than the other aldehydes. So when ozone is used in this advanced treatment process, when you're taking the treated wastewater and making it into drinking water, you produce all these aldehydes. Fortunately, some of them are removed during reverse osmosis. They're low molecular weight neutral compounds, so about half of them are removed, and some of them are removed during this UV peroxide process. The other thing we saw is that if you follow this ozonation step with something called BAC, this is biological activated carbon filtration. When you let microbes grow on activated carbon, the microbes break down these aldehydes. Because they're such strong electrophiles, they actually react with the microbes themselves, so the microbes have an easy time breaking them down metabolically. So we found that if you apply this UV treatment process after reverse osmosis, it's very efficient. We could relate the kinetics of the reaction. So here's 1,4-dioxane, a compound with moderate reactivity with hydroxyl radical. You can see that under typical conditions, we see about 75% removal of this. Most other compounds react with hydroxyl radical at rates faster than that of 1,4-dioxane, so usually approaching the diffusion-controlled maximum of 10 to the 10th. So just about everything else is removed by 75 or 80 or 90%. But there are a few compounds of concern. So one compound of concern is acetone, a low molecular weight compound that can go through reverse osmosis membranes because it's uncharged and low molecular weight, and it has a relatively low reaction rate constant with hydroxyl radical. So if someone spills a truck of acetone in a city, most of it will make it through the sewage treatment plant, and then if it goes into our advanced treatment plant, most of it will make it through the reverse osmosis membrane, and most of it will make it through the UV peroxide process. So places like Orange County in Southern California are starting to pay more attention to making sure that if people use acetone within their wastewater collection area, that they take care of it and don't put it down the sewer at the end of the process. So chemistry students in here, don't put your acetone down the sink because it ends up back in your drinking water later. Another compound, another class of chemicals is TCEP. This is a flame retardant, a phosphorus-containing flame retardant that often gets put into people's clothing or put into different products and plastics. This stuff, it doesn't break down with hydroxyl radical. Luckily, it's largely removed during reverse osmosis. Okay, I want to tell you about my third adventure in water treatment. My third adventure in water treatment is small-scale treatment. So you're probably sitting here saying, gosh, 110 gallons a day of water, that has to be treated. That's a lot of water. It all has to be treated to drinking water standards because that's the infrastructure that we've built in our cities to move water around. What if we could treat the water just before we use it? Now, for years, people would say, like when we have arsenic in people's drinking water, or when we have water that we collect from the roof of a building, we should be able to treat it and use it directly. And we should be able to install so-called point of use or point of entry water treatment systems, small-scale water systems that says that basically the water that comes into your house through the pipes doesn't have to be all that clean because you can do a little bit more treatment just before you use it. But that was always seen as like a step backwards. We'd worked so hard to make clean drinking water. We worked so hard to build the confidence that we could drink the water coming out of our tap. We didn't want to fall prey to people who try to psych people out and make them drink bottled water. We wanted to support the system of drinking tap water. But I see an opportunity now for us to start to return to this issue of small-scale water treatment systems because there's a new enthusiasm for advanced treatment at a small scale in buildings. This is a photograph of an actual building-scale water treatment system built in the Salesforce Tower in downtown San Francisco. So if you look across the bay at lunch and you see the very tallest building on the horizon, that's the Salesforce building. And in the basement, they have this water recycling system. And this water recycling system takes the water that comes down the toilets and the sinks in the building and subjects it to a biological treatment, just like a conventional wastewater treatment plant, filtration, reverse osmosis, and UV treatment. You can see the reverse osmosis cartridges here in white in the foreground, and the back wall, there's a UV treatment system. They're not adding peroxide yet, but they could easily do that. And then they use that water to flush the toilets. It's clean water. It's a fancy building. They didn't want to take a risk that someone would get sick or that the water would look funny. But I'm almost ready to drink that water because it's gone through the same sorts of treatment processes that happen at the advanced treatment plants I've been working at for years. So I've been thinking with my colleagues about building a so-called net zero water house, or think about it like as an off-the-grid house. And we did this analysis last year where we looked at several different types of apartment buildings, and we said, if we put current off-the-shelf technologies for water recycling, just for toilet flushing and showers and washing machines, and if we captured the rainwater that fell on the roof of the building and used it as a drinking water supply, what would it cost? Would we run out of water because we didn't have enough during the year? How much electricity would we use? And what we found in our analysis is that if you live in North America or Western Europe, this could be a less expensive technology than the existing way that you get your water because you pay relatively high tariffs for water delivery in your building. In Eastern Europe and South America and parts of Asia, water's a lot cheaper, so it doesn't make sense yet. And this was only using existing technologies. So we see a lot of potential for development of treatment technologies that allow buildings to operate autonomously without a connection to the main water supply. Now, I don't think that's going to happen very quickly. We're going to need water in our cities for firefighting. We've built a lot of infrastructure. We don't want to abandon it. But as water scarcity becomes greater, this starts to become an option. And one of the things that I'd like to do is I'd like to start using miniature versions of that advanced water technology that I showed you before, the UV peroxide process, may be preceded by reverse osmosis. But the problem here would be that I'd have to show up every few weeks and add more hydrogen peroxide. And at a big treatment plant, like in Southern California, you can have trucks coming in bringing in hydrogen peroxide, or you can have great big tanks of it. But in the basement of a building, you wouldn't necessarily want to do that. So what we're starting to do is we're starting to use electrochemistry to make the reagents we need in the water treatment process like hydrogen peroxide. And what we've built here, this is just one example of a system where we use a very inexpensive form of paper, essentially like a carbon paper. One side of the carbon paper is coated with graphite. The other side is coated with the Teflon-like material. The Teflon-like material faces the water, so the water doesn't move through the paper. The other side is exposed to the room, and the oxygen in the room air diffuses into that electrode. And then we reduce it by 2 electrons and make hydrogen peroxide. And the hydrogen peroxide, which looks just like a water molecule, diffuses out the other side into the water. And you can see here our production of hydrogen peroxide in this electrochemical process, where we achieve Faraday efficiencies often in excess of 80%. So nearly like theoretical maximum amount of hydrogen peroxide we produce. And then we could either shine a UV light at this and make hydroxyl radical, or we could find another way of doing it. And the way that we've stumbled upon to do this is using a stainless steel scrubbing pad. So if you've ever seen like those Brillo pads you have at home, we could take one of these and make it into an electrode, because on the surface of the stainless steel you get iron oxides. And these iron oxides act as catalysts, and they turn the hydrogen peroxide into hydroxyl radical. And the reason we like it is that we can stuff it inside of a cylinder and make it into a 3D electrode that actually has a very high surface to volume ratio. Here's an example of some of the work that Yanghua Duan has done. He's sitting here in the 5th row if you want to talk to him about it. But basically, we see yields of hydroxyl radical often approaching 50 or 60%. And if you remember when I talked about the Fenton reaction from my first adventure in water treatment, I was only seeing efficiencies of 1 or 2%. So we've got something that works well. And ultimately, the issue is to take this system that we have now as a laboratory prototype and turn it into something that looks like the under-the-sink reverse osmosis units that people are starting to install in their homes. Imagine this electrochemical treatment process after the RO system. You could treat just about any water that you find. Tap water, groundwater, water that you take off the roof of a building. It could all be treated to remove the pathogens and the organic chemicals. So in summary, just a few final thoughts. I told you today about chemical oxidation. I told you that it's a powerful tool to treat organic chemicals that threaten the water supply. So it's a basic idea from freshman chemistry of using strong oxidants. The mechanistic understanding of the radical formation pathway can provide insight into the ways of increasing the efficiency of the process. I didn't talk a lot about that today, but really what we spend a lot of our time thinking about is how to get a higher yield, how to turn that hydrogen peroxide into hydroxyl radical. It's pretty important to minimize the formation of toxic transformation products. I didn't really talk a lot about it. I talked about the unsaturated aldehydes, but if you're going to mess around with oxidants, you better not make toxic byproducts, and we spend a lot of time thinking about that. And finally, water treatment and recycling, the last 2 adventures I told you about, they reduce society's water footprint. So back to the beginning of that water footprint, and that's critical in a time of climate change. So I wanted to acknowledge my students and postdocs whose research I've talked about today. Several of them are here today, but some of them have graduated since. Collaborators at Berkeley and at other universities, and my sources of funding. And then finally, I don't expect you to copy this down, but it'll be on the video. These are the references I talked about during the talk, so if you're curious and want to read them, I write them at the level that a first-year, we write them at a level that a first-year college chemistry student could understand, because we're often working with engineers and practical people who need to understand at a basic level. So it should be accessible to anyone who's in the audience today. And with that, thank you for your attention.
Thank you.